So, welcome back students. So, we are basically discussing a combination of different strategical viewpoints, and we said that functional group based strategies, transformation based strategies, functional group, transformation and starting material based strategies, you can always couple together to access medium sized target molecule. Now, here the first problem which will be analyzed in this lecture, the structure is this compound. Now, this compound, if you see, it is a alpha beta unsaturated ester, and the starting material was given to you. The starting material I will be given to you, and I said you use this compound as well as acetaldehyde as a starting material. So, target molecule is this, your starting material 1 is this, starting material 2 is this. Now, let us see where this acetaldehyde and this compound can be coupled to give you this part. We will initially analyze the standard retro pathway by formulating this kind of things. So, CH2 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 CH2, if you have a aldehyde something like this, and if it is possible you can do a Wittig transformation, is very much possible, and we say the Wittig things will be using this kind of halide. Now, this intermediate, if you now count the carbon, is having this part is coming from this part, okay, 1 2 3 4 5 1 2 3 4 5, and the remaining part is basically your acetaldehyde. So, now you can say that this can be in principle disconnected by this way, that you take a acetaldehyde anion, this is acetaldehyde anion CH2 minus, and then you react with this electrophile. So, basically you need to do a alkylation on acetaldehyde. So, normally acetaldehyde alkylation is not very well known. Not very well known means acetaldehyde usually like alkylation you are often called about ketones. Ketones can be easily alkylated, you can generate the enolate very easily by this metal and do the alkylation with this electrophile. Now, acetaldehyde, it is a tricky situation. Acetaldehyde probably will definitely enolize and will give you a vinylic alcohol. Now, vinylic alcohol is very unstable. So, normally this compound will always try to be in this form, this keto form in most of the time. Now, here we will be using a particular strategy named as enamine alkylation. I am sure probably we have talked about these strategies earlier when we talked about Stork enamine methods. Now, enamine alkylation for these compounds like this acetaldehyde is very useful. So, what initially was done? You treat this compound with some primary amine, and initially you find that this acetaldehyde reacts with this primary amine through a condensation reaction to give you imine. Now, this imine, when you subject it to base, imine are basically equivalent of ketone. So, this acidic hydrogen will be now picked up, acidic hydrogen will be now picked up, and this imine will be now converted to a enamine. So, we will basically get this ANLI. So, imine now converted to enamine. Now, enamines are basically nothing, these are aza-enolate. Probably this aza-enolate method we have already discussed earlier, but again this aza-enolate is very interesting. Now, this aza-enolate, if you react with a electrophile this things will again come back to react here, and basically will give you this N, this tertiary butyl will remain here and will give you CH2E imine back. Now, you can hydrolyze this imine to get the corresponding aldehyde back. Now, compounds like acetaldehyde, as I said, which are not very easily analyzable, you can initially convert this acetaldehyde to its corresponding imine, which I have just explained in the earlier slide. So, now you react with LDA and instantly put this electrophile, which is prenyl bromide. Now, you see, once this prenyl bromide you can use, first you will get this one, and then this imine can be easily hydrolyzed to H3O plus. So, you can basically generate this compound, which is nothing, a acetaldehyde which have been alkylated with prenyl bromide. So, now we are very close. Now, we need to do a Wittig reaction with this particular elite or the salt. To do this Wittig reaction, which seems to be pretty much straightforward, and you come to this target molecule. Now, this Wittig salt can easily be generated, this Wittig salt, by using this bromo compound with refluxing with triphenylphosphine, which will be giving this required Wittig salt. So, this way this enamine alkylation is very useful, and you can combine it with this particular electrophile. Here we use the prenyl bromide. So, try to continue the similar strategy. Next, we will analyze another problem. So, more problem you solved, your ideas will be coming out. So, you need to solve as much problem as you can. The target was basically this conjugated diene. The starting material, which I also give it here, I said this compound, starting material. Now, if you now do a skeletal analysis, as I said, this skeletal remains same. The right hand side skeleton of this molecule was remain similar to the starting material, fine. Only thing is, next you need to do something. So, what I now initially propose that okay, we will keep it this way, and we say okay, as this ketone group is there, we will do a Wittig kind of olefination if it is possible here, a P plus and other things. So, if a Wittig reaction, so it is basically a intramolecular Wittig reaction to make this olefin. So, we all often use intermolecular Wittig. Now, we will be using a intramolecular Wittig. Now, we say the how you can get this Wittig salt or Wittig elite. Now, we say if you having a, if you now disconnect the original starting material with this particular Yes, it is quite possible. So, this starting material is known to you, and this starting material probably you can make it by basically corresponding this compound, which you can easily make from this compound by Apple reaction. So, now start the forward synthesis and how the synthesis can be achieved. So, initially I said you are having this alcohol, you do a double Apple reaction or you can do a single Apple reaction, probably we will do a stepwise thing, or so that no regiochemical issue is coming in between. So, we will do a simple protection first, we do a TBS chloride protection 1 equivalent by McDougall's protocol. Okay. So, then you get a OTBS CH2OH, fine. Now, we do a Apple reaction, Apple TPP and CVR4, you basically get the OTBS CH2Br. Now, here you react your starting ketone and take this as a electrophile, generate the enolate from this thermodynamically more stable enol, and then you do the alkylation. OTBS. So, now basically remove this TBS with PTSA, that will give you the alcohol. Then you do this Apple again. So, now what we will basically get this Br, double bond O will remain here, do this methyl, you put these things. Now, here we will reflux with triphenyl phosphine to get the corresponding Wittig salt, and we say this Wittig salt will be P plus, this pH3 was not written here due to space problem, and then you find this compound, ketone is there, you are having this thing. So, this structure probably you can easily write it out. Now, we will be subjected to a base butyl lithium and do a intramolecular Wittig, This intramolecular Wittig will now close the ring, will give you this product. So, this target was basically achieved by using this as the main starting material. So, what transformation we have used? We mainly used the couple of interesting transformation. We use a protecting group based transformation, we protect a hydroxy group, we do a Apple reaction to convert hydroxy to bromide, then we do a thermodynamically controlled alkylation, we remove the protecting group, we do a one round of Apple further to come to the bromo, we convert this bromo to corresponding phosphonium salt, then you close the ring by a intra-Wittig. So, we basically combined couple of transformations together and then you can access the particular target molecule. Next, we will try to analyze a very simple problem, probably the last problem in this class, but let us try to analyze it. this is a carboxylate acid salt and 3 hydroxy group are there on the cyclohexane subject. The relative stereochemistry was also given. The starting material which was given to you is this starting material, cyclohexene carboxylic acid. Now, we will say the retro which I will be doing now, will try to write the cyclohexane ring in a different way, and then we say that this compound can easily be made if you having this lactone which you can easily opened up through sodium hydroxide. Now, see the relative stereochemistry, this CO2 is above, this OH is above. So, this is 1-3 relationship, 1, 2, 3. If they make a lactone which looks like this and then OH is below, OH is below. So, if you have this lactone you can open it up. Now, how this below OH you can basically introduced. We basically propose that if you have a double bond here, the hydroxylation by a osmium tetroxide will takes place from the bottom phase, as top phase is blocked by this lactone ring. Okay. And then we try to figure it out that this lactone, this particular iodolactone can give you this olefin by simple E2 elimination. Okay. Now, this iodolactone can be constructed from this carboxylic acid through a iodolactonization. So, now we will analyze the forward path and how this things has been done. We first write this starting material in the 2-dimensional form. Then you say that this compound is subjected to the iodine and sodium bicarbonate, the standard condition of iodolactonization. We write this compound in a half chair form to give you little bit structural viewpoint. Now, initially this iodolactonization will be formed in this way. You basically have this iodonium ion here. Now, the CO2OH minus will attack to this double bond from the below side, and then you now, okay, though we are not talking about stereochemistry in detail, but in principle you will get this kind of, because if it attacks here, this axial, this iodo now comes here, is basically 1-2 anti. The attack SN2 type of attack, it comes in a backside attack to give you this compound. Now, is having a hydrogen here, this is having a hydrogen here. So, base, anti-peripheral arrangement, E2 elimination nicely takes part. Now, if this E2 has to be taken place, the ring will not be now chair, it will be again half chair kind of thing. That is what we put the half chair lactone. In this half chair, this axial blocks the top phase. So, now you use the osmium tetroxide, this was the OH now comes from the bottom. So, this compound is basically nothing but if you can write it in a 2-dimensional stereochemistry, it is OH here, it is OH here, it is O, it is C double bond O. Now, what you need to do? You basically hydrolyze this compound with sodium hydroxide. So, sodium hydroxide will be acting as a base and it will touch the lactone ring and it will hydrolyze this lactone with its corresponding carboxylate salt. This is the target molecule. So, eventually what are the transformation we used to access the entire thing? We said the transformation we used a iodolactonization, starting from a 3-cyclohexene carboxylic acid, we do iodolactonization. The stereochemistry part was has to be taken care, because initial iodolactonization you forms the iodonium ion, initial starting material we assume a half chair kind of conformation. Hydroxy comes from the back side and gives you a diaxial thing, and then this lactone is basically now having a cis, both the CO2H and OH are cis to each other. You put a base. Now, iodo and hydrogen now in 1,2 anti-peripheral arrangement, you get a new pi bond. Osmotic reduction mediated dihydroxylation, you get this OH here, and which is basically nothing, the relative stereochemistry, this O and CO both are above the plane and this OH are below the plane. Now, you hydrolyze it to sodium hydroxide, you can basically end up with this particular compound. So, there are many similar kind of reaction, but try to figure it out that as stereochemical issues, if there are stereochemical issues which need to be addressed, you have to taken stereochemical issues need to be addressed properly. I mean, if your molecule has some stereocenter, you need to think about very carefully, and probably we can earlier we have talked about that if you having a free hydroxy group, you can immediately protect this hydroxy group as its benzyl or PMB ether very easily. Now, I am saying that you just treat this compound with benzyl bromide or PMB bromide, react with a base sodium hydride, you can immediately get is O benzyl or O PMB, which is the very good protecting method. Now, group E, we have not specified what kind of group is this. Now, I say I am giving you a compound whose structure is this, is basically a ethyl lactate, and as stereocenter is given is a 1, 2, 3, hydrogen is on back side. So, this compound is R. So, is R ethyl lactate. Now, I am saying that if you react this compound with sodium hydride and benzyl bromide, will you get the same benzyl ether? My answer is no, because sodium hydride seems to be a strong base. The hydrogen which is available here is adjacent to a carbonyl group. Now, sodium hydride, it picks up this hydrogen fine, but in addition it may pick up this hydrogen also. So, basically this hydrogen can be picked up and this stereochemistry of this particular center may get changed. You will basically getting a epimerization of this particular center. That is absolutely serious issue, needs to be considered. If you treat this molecule with strong base like sodium hydride, you will find that these things basically epimerized to give it the enantiomer. So, this compound is, if it is R, this compound is S. So, under the reaction condition, the enantiomers are basically in a dynamic equilibrium. So, if you start with R, you might get this product, but the center might be inverted. So, in those cases you need to find it out a relative mild protecting group condition where the benzyl or other groups can be protected. This was we did not discuss earlier when we talk about protecting group chemistry, and I thought we will be discussing when we discuss the functional group based strategies. Now, this case we will basically using a reagent whose name is benzyl imidate. Benzyl imidate or PMB imidate is a pretty mild reagent which you can easily prepare by reacting with benzyl alcohol with trichloroacetonitrile. Now, you need pretty mild base like potassium carbonate to generate this enolate, generate this imidate. So, what happens this basically reacts here and initially will give you this imidate. Now, this imidate whose structure is basically pH CH2O double bond NH CCl3. It cleaves in presence of a pretty mild acid like camphor sulfonic acid, and it exists as a this first basically kind of a protonated, this first kind of protonated, and then it will give you a simple benzyl kind of cation with these things like this oxygen is now shifted to give this things protonated. So, basically you will get CCl3 CO NH2, which is basically trichloroacetamide, and this compound name is trichloroacetonitrile. So, now as this benzyl cation is free, now if you react with this cation, it will basically react under this condition and will give you a benzyl protected thing. Similarly, you can also create PMB imidate whose structure is also similar like this. So, if now we have to tackle some issues that wherever you are having a acidic hydrogen which is mainly possible if you have electron withdrawing group, then you can easily protect this hydroxy group as this benzyl or PMB ether by using benzyl imidate or PMB imidate. So, base condition you have to avoid it to suppress the epimerization. Now, very efficiently you can protect this hydroxy group as this benzyl and PMB ether with absolute ease, and the stereochemical information will be retained. So, next class we will be talking about particular these aspects, and I will based on this information we will formulate our next problem, which is again basically a combination of starting material, functional group and transformation based approaches. So, till then have a good time and goodbye.